What if you could squeeze 10 pages of text, every character, every nuance, into a single image and still read almost every word perfectly?
Welcome to Artificial Intelligence, Papers and Concepts, curated by Dr. Satya Malik. I'm Jack Malik.
And I'm Sophia Lane. And yes, just so you know, for complete transparency, we are both AI-generated hosts guiding you through this deep dive into the latest research.
And today, our mission is quite specific. We're diving deep into a paper introducing DeepSeek-OCR, focusing on this really interesting concept they're calling context optical compression.
Right, so this isn't just about another OCR tool, is it? It sounds like we're exploring something more fundamental, maybe a shift in how long context LLMs could work.
Precisely. It's about dissecting how the visual modality, so turning text into an image, can actually function as an incredibly efficient compression medium. The core goal for you, the learner, is to understand how this approach might offer a scalable way around that huge computational challenge LLMs face when dealing with really, really long texts.
Okay, let's unpack that challenge because it really is the fundamental bottleneck, isn't it? We know LLMs are amazing, but feed them a massive document, say 100 pages, and the costs just, well, explode. Why exactly is that cost so prohibitive?
Yeah, the reason is baked right into the transformer architecture. You see, when the model processes a sequence, like a document, it uses self-attention. Every single token has to look at every other token. So if your document has n tokens, the computation scales quadratically. That's n squared.
N squared. Okay, so double the document length. You don't just double the cost, you quadruple it.
Exactly.
And going from, say, 1,000 tokens to 10,000 tokens, that's 100 times the computational load.
Right.
Wow, it's just not a sustainable way to scale for long stuff.
Precisely. And that's why this paper's insight is, well, I think it's quite brilliant. It suggests maybe the solution isn't just a better text transformer, but changing the modality altogether. The core idea of optical compression is that a single high-res image of text holds all that rich information, but uses way fewer vision tokens compared to the equivalent digital text tokens.
Okay, let me just make sure I'm tracking the basic mechanism here. So in a standard LLM, a word like bottleneck might be 1 token, maybe 2. A whole page could easily be, what, 1,000 text tokens?
Easily.
But if we take a picture of that page, the vision encoder can summarize that whole page into, you're saying maybe just 100 vision tokens.
That's the whole idea, yes.
Yeah.
Because one vision token is information dense. It knows about shapes, positions, context. It can effectively stand in for maybe 10 or even more text tokens. And that massive token reduction immediately helps with the computational cost, making long context processing potentially much more affordable.
And using optical character recognition, OCR, is kind of the perfect way to test this idea scientifically, because you get a direct, measurable comparison.
It's exactly right. OCR gives you that natural compression-decompression cycle. You compress the text into vision tokens, then the decoder has to decompress it back into readable text. This provides really clear quantitative metrics like character precision, accuracy. And DeepSeek-OCR, it's a vision language model, a VLM, specifically designed from an LLM perspective to be the proof of concept for this vision text compression idea.
Okay, so we've got the problem, the n squared bottleneck, and the potential solution. Optical compression via vision tokens. Let's get into the numbers because that's where the proof really is. We're looking at the DeepSeek-OCR architecture. It uses a special DeepEncoder for the compression part, and then the DeepSeek 3B MOE A570M decoder to reconstruct the text.
Yep.
And the key metric you mentioned is the compression ratio. Basically, the number of original text tokens divided by the number of vision tokens used.
That's the one. And the results on the Fox benchmark are pretty telling. This benchmark uses standard English documents, maybe 600 to 1,300 text tokens each. This is where they found the boundary for what you might call near lossless compression.
Near lossless. And that boundary is around 10x compression. What were the specifics?
Right. So when the compression ratio was kept within that 10x limit, for example, they hit 9.7x compression using only 100 vision tokens for documents that started with nearly 1,000 text tokens. The OCR decoding precision was hovering around 97%.
97% precision at almost 10x compression. So wait, that means reducing the computational token count by 90% while only losing about 3% of the information fidelity. That's really impressive. But I guess for some applications, maybe industrial ones, even a 3% loss could be too much. Does the paper talk about that trade-off?
Oh, absolutely. The whole design is flexible. A user can decide to scale the vision token count up or down. If you need higher fidelity, you reduce the compression ratio a bit, say aim for 8x instead of 10x by using more vision tokens, and you likely push that accuracy closer to 99%. What the 97% result really does is validate that vision is an effective medium for high-ratio compression. It works.
And they didn't just stop at near lossless, did they? They pushed the boundaries further.
They did, yeah. They really wanted to see what happens under extreme compression. So they cranked the ratio up towards 20x, specifically at 19.7x compression, which meant using just 64 vision tokens for those same long documents. Well, the accuracy dropped significantly, as you'd expect, but it was still viable, around 60%.
60% accuracy at almost 20x compression.
Yeah, 59.1% to be precise. It shows that even with a severely compressed visual input, the language model decoder can still pull out a meaningful, lossy but useful summary.
Okay, let's pivot to how this performs in practice, the OmniDoc bench results. How does this efficiency stack up against models people are actually using now?
Well, it translates into state-of-the-art results, but using way fewer resources. For instance, DeepSeek-OCR actually surpasses models like GOT-OCR 2.0.
Okay.
And GOT-OCR 2.0 typically needs around 256 tokens per page. DeepSeek-OCR beats it using only 100 vision tokens.
Right, less than half.
And then when you look at their really high-resolution modes, they have these names like Gundam mode, using fewer than 800 vision tokens per page. DeepSeek-OCR outperforms MinerU 2.0.
And MinerU 2.0 needs?
MinerU 2.0 needs almost 7,000 vision tokens for similar high-res tasks.
Wow. 7,000 tokens versus fewer than 800. That's nearly a 9x efficiency gain just in token count for those complex documents. That reduction in tokens is where the time and cost savings really come from?
It absolutely is. And the paper gives good guidance on this too, like simpler documents, think presentation slides, basic letters. They don't have that many text tokens to begin with, so they only need maybe 64 vision tokens for really high performance.
But the complex stuff, the things that really challenge OCR systems, they need more horsepower, right?
Yes, definitely. Think about newspaper pages. They're dense, complex layouts, often with 4,000, maybe 5,000 text tokens tacked in. For those, you need the high-resolution modes like Gundam or Gundam Master.
Right.
That pushes the vision token count up, maybe several hundred. But crucially, even then, the compression ratio compared to the raw text input is still very high. It makes processing diverse documents practical and optimized.
So if compression is the heart of this, then the DeepEncoder must be the engine doing the heavy lifting. And it had some really tough requirements, almost contradictory ones. It needed to handle super high resolutions, keep activation memory low, and produce very few vision tokens.
You're saying current open source encoders just can't do all three?
Exactly. That's the challenge. Existing high-res models often use attention mechanisms that just balloon the memory usage and compute cost as resolution increases. DeepEncoder gets around this with a really clever serial connection of components.
Okay, walk us through that architecture. How does it work?
So it connects two major known components in series, but with a crucial compression step in between. First up is the visual perception part. It uses SAMI base, that's the segment anything model. This part relies on window attention, which is local, computationally cheaper, and great for picking up fine details in high resolution.
But the output from that first stage is still pretty big, isn't it? You said 4096 patch tokens from the image. If you fed all 4096 directly into the next stage,
you'd hit that n-squared bottleneck right away.
Yeah.
Exactly.
So the next stage is the visual knowledge component. This uses CLIP large, and it needs dense global attention to understand the overall page content and context. But running global attention on 4096 tokens, that would completely kill the low memory requirement and efficiency goals.
So the 16x convolutional compressor they put in between is literally controlling that bottleneck.
Precisely. It acts as the bridge. It takes those 4096 high-res patch tokens coming out of Sandbase and squashes them down to just 256 tokens. And the key is this compression happens before the tokens hit that computationally heavy CLIP global attention layer. It's a really smart design to keep memory manageable while still getting the benefit of high-res local perception.
That really is a neat piece of engineering around a core constraint. And speaking of efficiency, the decoder part, the bit that reconstructs the text, that's optimized too, right? Using mixture of experts.
Yes, the DeepSeek 3B MOE decoder. So for the listener, a mixture of experts model can be very large in total parameters, 3 billion here, but it's sparse during inference. It only activates a fraction of those parameters, maybe around 570 million, for any single task. So you get the expressive power of a big model, but with the speed and efficiency closer to a smaller one. Perfect for quickly turning those compressed vision tokens back into text.
The sources also mentioned flexibility being key for real-world documents, hence the different resolution settings. Tiny, small, base, large, Gundam.
Absolutely essential. Different documents just need different token budgets. And to handle those really extreme ultra-high-res inputs, like those newspaper images we talked about, they use what they call dynamic resolution modes like Gundam. Instead of trying to process one massive image, they use a tiling method. They break it into, say, 2 to 9 tiles. This lets them handle enormous resolutions without creating an unmanageable number of tokens, keeping the whole system scalable and efficient.
Okay, so beyond just proving the compression concept works, this model seems to have serious practical value just for generating data alone. The production scale mentioned in the paper is, well, it's kind of mind-boggling.
It really could change things for AI research and development. DeepSeek-OCR can churn out large-scale pre-training data, the stuff you need to train the next big LLMs and VLMs, at over 200,000 pages per day on just one A100 GPU.
200,000 pages a day.
And if you scale that up, say to 20 nodes, you're talking about 33 million pages per day. That's an enormous amount of high-quality training data, enough to potentially bootstrap the next wave of general AI models.
But it's not just extracting basic text, is it? The paper talks about deep parsing capabilities, what they call OCR 2.0 data. What kind of complex stuff can it pull out that normal OCR misses?
Right, it goes way beyond just text strings. It handles complex figures within documents. For example, it can parse charts and output them directly as structured HTML tables. That makes the data immediately usable by machines. It can recognize chemical formulas and convert them into the standard SMILES format, which is huge for chemistry and drug discovery.
And it even gets into visual reasoning.
Yeah, it can understand and copy the structure of simple geometric shapes. It also handles general vision tasks within the document context, like writing dense captions for photos embedded in the page or doing object detection and grounding. And importantly, because they gather data from diverse PDF sources worldwide, the model handles nearly 100 languages, so it's pretty globally applicable.
Okay, now let's get to the final concept in the paper, which might be the most thought-provoking one, connecting this whole optical compression idea to memory, like biological forgetting.
This is where it shifts from clever engineering towards suggesting a fundamental cognitive architecture. The problem with LLMs having truly unlimited context isn't just the compute cost. It's also about relevance and retention. Our brains don't store everything perfectly forever. Older memories fade, they get summarized, lose detail.
Right, and this optical compression approach seems to mimic that process somehow.
Exactly, because optical compression allows for controllable information loss. You can quantify it. Imagine this. New contexts, the stuff you just read, are kept at high resolution, high fidelity using more vision tokens. But older context documents from last week, last month, you could progressively downsize them, visually blur the image representation.
So blurring the image naturally reduces the detail, which means the vision encoder needs fewer tokens to represent it. It's like how our memories lose specific details over time, but keep the gist.
Precisely. This controlled optical decay offers a really interesting practical path towards potentially unlimited context in LLMs. Instead of just chopping off old context arbitrarily, which is what models do now, you allow older information to gently blur through higher compression ratios. This continuously reduces the token burden of that long tail of memory. It's a really elegant concept, I think.
So summing this all up for the listener, what's the main takeaway from this deep dive? DeepSeek-OCR seems to have strongly validated this idea of context optical compression.
Yeah, the core finding is that the visual modality isn't just for pictures of cats. It's a powerful tool for efficiency. It showed we can get up to 10x near lossless compression of text contexts. This really could open the door to efficiently processing documents that are thousands of pages long, getting us past that stubborn n-squared compute bottleneck.
And maybe the most exciting part, because vision tokens give us this controllable way to lose information. Through blurring, through compression, it could fundamentally change how we tackle long context challenges. So the final thought for you to consider is this. If we start moving away from purely digital, perfect recall systems and towards models that incorporate a kind of optical decay, could this approach fundamentally reshape how LLMs manage long-term memory? Could it lead to genuinely unlimited context windows? It's a really powerful new direction to think about.
Definitely something to mull over as these AI systems keep evolving.
Thank you so much for listening. This podcast was sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai. See you in our next episode.